Well, you ready for a little fun in the lab? I thought you might be missing this. So we decided to videotape a few of the labs here in my barn. And so the one that you missed this last time was the evaluation of the ideal gas constant. And so you can see that it doesn't really take a whole lot of equipment here to measure a very important constant in the study of gases. But before we do the experiment, probably should have a little background on the ideal gas equation and the derivation of that constant R. So here you go. Well, figuring out the ideal gas constant is actually not much of a trick. When you think about the fact that in the last lab, we looked at the relationship between the volume of a gas and its absolute temperature, which was Charles' law, that volume was proportional to the absolute temperature. We also looked at Boyle's law, which said that volume was proportional to 1 over the pressure. Well, today we want to introduce Avogadros Law, which says that the volume of the gas is proportional to the number of moles of gas present, which we use the symbol N for in the ideal gas equation. Now, Avogadros' law basically boiled down to this. He said that 1 mole of any gas. Boy, I missed the click of chalk on a chalkboard. 1 mole of any gas will occupy 22.4 liters at 0 degrees centigrade and 1 atmospheric pressure. Now, they refer to these conditions, by the way, as standard temperature and pressure, STP conditions. You see that a lot in the gas law chapter. But this makes gases kind of unique. I don't know if you remember, but back at the beginning of the semester, chances are your lecture instructor brought in a sample of different quantities of moles of solids. And for instance, a mole of sugar is a lot. It's 3/4 of a pound of sugar. But a mole of carbon atoms is only 12 grams, is very small. And so the size of a mole of a solid would depend primarily on how big the atom is or how big the molecule is, because they're all packed in there right up against each other. But with a gas, the volume occupied by a gas is more of a function of how far apart the gas molecules are. The actual physical size occupied by the gas molecule is insignificant compared to the space between the molecules. And the only thing that dictates that space is what temperature and pressure the gas is at. So if we have 2 different gases at the same temperature and pressure, the amount of space between the molecules is going to be the same. And the size of the molecule itself will become insignificant. Well, if we choose a standard temperature and pressure, then all gases should occupy the same volume. And that volume turns out to be 22.4 liters at standard temperature and standard pressure. All right, well, we can combine all of these proportionalities into one larger proportionality. Let me just erase the board and I'll show you. I'll fade out and fade in. Okay, so this explanation about the ideal gas equation, pretty simple. I mean, we said before, we have Charles' law, Boyle's law, and Avogadros' law that represent different proportionalities to the volume of a gas. If we combine all those proportionalities into one, we get that volume is proportional to the moles of gas times the temperature absolute divided by the pressure. Well, proportionalities are real nice. I mean, the fact that the volume is proportional to all 3 of those, meaning that if 2 were constant, you can see that there's Avogadros' law. If these 2 were constant, there's Charles' law. And if these 2 are constant, there's Boyle's law. But proportionalities are good for comparisons from one set of conditions to another set of conditions. A lot of times you want to do something statically, meaning just give me the answer right at this set of conditions. Well, it'd be nice then to have an equality here, but to have an equality, we would need kind of a proportionality constant. For instance, here's an example. If I told you that 1 was proportional to 3, the same way 2 was proportional to 6, the same way 3 was proportional to what? Well, your brain is already telling you what the proportionality constant is here. There's a fudge factor. You can see that the second column is 3 times the first column. So your brain has already figured out that this is going to be a 9. Meaning that we could have replaced this proportionality symbol with something like, 1 times a fudge factor, let's use a little f for that, would equal the 3. Well, once you saw a couple of these in a row that you knew worked, you immediately came up with the idea, well, that little f must be a 3. The fudge factor was easy. So that told you that this had to be a 9. Well, if that's the case, then why couldn't we put a fudge factor in this proportionality that volume is equal to, and let's use an R for our fudge factor since it's kind of already been used, R times NT over P. Well, all we really need then in order to find the actual value of R is, like in our earlier example, one set of numbers here that we know already works. I gave you a couple of sets that you knew worked before your brain came up with the fudge factor, but we do have a set of numbers that we know works for all gases. From Avogadros Law, it says that if we had 1 mole of gas at standard temperature and standard pressure, it would always occupy 22.4 liters, and that would work for all gases. Well, in that case, let me just rearrange this equation to solve for R. Let me fade out and in here. We'll get this rearranged. Okay, although you most often see the ideal gas equation as PV equals nRT, if we rearrange this and solve for R, you can see the 4 pieces of information that we would need to calculate R. And using Avogadros' hypothesis, we can plug in his 22.4 liters magic volume at standard pressure and temperature with 1 mole and find out that that R value should come out to be 0.0821 liter atmospheres per mole K. Again, that stipulates that the pressure has to be measured in atmospheres, the temperature in Kelvin, and naturally moles, and the volume in liters. So we already know this proportionality constant. What today's lab is going to do is show you how easy it is to just generate a sample of gas, measure its volume, measure the pressure you collected it at, the temperature you collected it at, and if you can figure out how many moles of gas you generated, that ratio of those 4 should equal R. And so we're going to generate a little magnesium gas today, and we're going to collect it in a eudiometer tube by water displacement. And I'll show you the equipment here in a second. But the volume of the gas is very easy to measure if we just collect it in a device that has milliliters marked on it. The pressure in my barn today is 751 millimeters of mercury. Remember, standard atmospheric pressure is 760. Well, we're a little bit above the sea level here, and so it runs a little bit low, so 751 is not unusual. Well, we're going to collect our gas at that pressure in my barn. We are going to make a couple little adjustments to it because we're collecting it over water, so it's going to pick up a little water vapor that we have to adjust for. And the fact that when we collect it in the tube, a lot of times there's still water in the tube that sort of pulls on the bubble of gas that we've collected and stretches it out. We need to make a slight correction for that level difference. And I'll show you that here as we, after we do the demonstration of the actual experiment. But the number of moles of gas that we're going to generate today is very easy. We're going to generate it with magnesium. As a matter of fact, let me get a little bit of room here. And hydrochloric acid to make magnesium chloride and hydrogen gas. Well, a little piece of magnesium is pretty easy to just weigh it on the balance and figure out how many moles you're going to actually use. You'll note here that for each mole of magnesium we react in this experiment, we get the same number of moles of hydrogen gas. So this is a very easy calculation to figure out how many moles of hydrogen gas we're going to actually generate today. And we've got some thermometers right here in the lab, so, or in the barn, that we can just measure the temperature at which we collected the gas. So again, this is a pretty easy, quick and dirty calculation, and all you have to do is just generate a small sample of gas under your conditions. Okay, well, let's run the experiment and collect some data. We'll put it on the report sheet, and then we'll come back and look a little closer at some of the adjustments that we had to make, like I said, to the pressure, and we'll calculate that value of R. Okay, well, here we go. I've measured out a couple strips of magnesium. I've got 2 of them weighed. One of them's 26 milligrams, 0.026 grams. The other one's 0.024 grams. That's going to be important to us later when we do the calculations. We also need an 800 ml beaker almost filled with water because we're going to collect the gas by water displacement in what's called a eudiometer tube. It's a gas collection tube marked in milliliters. So the first thing we want to do is make a little cage. I'm going to start with the 24 milligram piece. And I've got a little piece of nichrome wire, a little cage to hold our magnesium in. Now we're going to react it with hydrochloric acid, but the first thing I want to do is make a little cage here for the magnesium strip. I'm just going to wrap it in the wire just to hold it at the bottom of the eudiometer tube while it reacts, because magnesium is pretty light. If we just throw it in there with the hydrochloric acid, it'll float to the top, probably stick to the walls of the eudiometer tube and not react. And we also need a little hydrochloric acid for the reaction we're going to do. They tell you to measure 8 milliliters. Well, since my eudiometer tube is marked off in milliliters, I'm just going to pour in some concentrated hydrochloric acid. And if you're going to err, we got to err on the plus side. But that's pretty close to 8 milliliters of concentrated hydrochloric acid in the bottom of the eudiometer tube. Now I'm going to put some water in here, and I'm going to dribble it in slowly. This keeps the hydrochloric acid kind of down at the bottom of the eudiometer tube. It's a little bit more dense than the water. Get this completely filled up, right up to the top. Now I'm going to put the magnesium a couple inches inside the eudiometer tube and then wrap the remaining part of the wire around the bottom of the eudiometer tube. I want to top this off, make sure it's completely full, because I don't want to start with a bubble or anything inside the tube. And now I'm going to invert this into this 800 ml beaker I have here filled with water. And put the bottom of the eudiometer tube against the bottom of that beaker. Let me clamp it in place. I'll try to get a close-up of this later, but you can see the hydrochloric acid kind of swirling its way down through the water toward the piece of magnesium that we have here at the bottom of the eudiometer tube. I like to put the tube against the bottom of the beaker. That way it traps the hydrochloric acid in there and it doesn't dissipate out into the body of water into the beaker. And we get a nice vigorous reaction. Now when the hydrochloric acid hits that magnesium, it's going to produce some hydrogen gas, and as the reaction gets more vigorous, it'll create some pretty large bubbles. We generally collect about a milliliter of gas for each milligram of magnesium we use. That's what we found in the past. Since this was the 24 milligram piece that I started with, I'm anticipating somewhere around 24 milliliters. I'm going to fast forward this a little bit to the end so we can actually see the bubbles and then make a measurement of how much gas is actually in the tube. Okay, so you can see the reactions getting going now that the hydrochloric acid has reached the magnesium. I noticed earlier I said magnesium gas. I meant hydrogen gas. But as the hydrochloric gets more concentrated down here at the bottom, you'll see that the reaction gets a little bit more vigorous. We get some like 50-cent bubbles instead of all this little stuff. And then it'll abruptly quit as soon as the magnesium's completely reacted. I'll just stay here on this for a minute or so. We've only collected 2 or 3 milliliters of hydrogen gas so far. And you can see it's getting a little bit more vigorous now. There we go. Now it's getting more reactive. You can see a little cloud of magnesium chloride that's actually being produced, and there it abruptly stopped as the magnesium was completely consumed. Well, we'll let it cool a little bit and come back and take a peek and see what the volume was. So the reaction is complete, the magnesium's all gone, and it appears that we've got, wow, 24.5, I'm going to call it 24.54 milliliters of gas. Now, one other important piece of information we need is the height of the water that's still inside the tube here compared to what we find in the beaker. The height of that water, the weight of this water in here, is actually pulling on that bubble of hydrogen and stretching it out. So we're going to make a little adjustment for that. I'm going to set the ruler right on the surface of the liquid. We'll go up here and take a quick peek. It looks like the liquid's at about 248 millimeters above the surface of the water in the beaker. So we're going to use that piece of information in a little bit. Oh yeah, we also needed the temperature of the solution, which is holding at 22 degrees. Get that where we can actually see it. Yeah, it looks pretty close to 22 degrees Celsius. So let's put a few things on the report sheet. Okay, well, for our first trial, the mass of magnesium that we used was 0.024 grams. Now later we're going to need to convert that into moles anyway, so let's just do it. 0.024 grams divided by the atomic mass of magnesium, 24.3. Let's put that in scientific notation. And we're going to cheat a little bit here and use 3 significant figures. So let's go 9.88 times 10 to the minus 4th moles. 9.88 times 10 to the minus 4. That's a 9, by the way. All right, well, our initial eudiometer reading was 0. We had no air trapped, no bubbles or anything in our eudiometer tube. And it ended up at 24.54 milliliters. Well, the volume of gas we collected then was 24.54. I'll leave it to you to change that number of milliliters into liters. As a matter of fact, let me scooch this up a little bit so we can see everything. So again, I'll leave that up to you to change that from milliliters into liters. The barometric pressure today is 751 millimeters here in the barn. And we're only going to do 2 trials rather than the 4 that are listed here. So let me just go ahead and put the 751 in for our second trial. If you recall, when we took the ruler and measured the level difference between the water level that was in the beaker and that was in the eudiometer tube, that ended up being 248 millimeters of solution. So this is the data that we collected. Oh, also we collected the temperature. Now we'll come back and show how we're going to do all the calculations. I just wanted to give you an opportunity to get your report sheet out and go ahead and copy down everything that we've done so far. The temperature was 22 degrees Celsius. We'll have to add 273 onto that in order to get our Kelvin temperature. So I believe that's everything that we collected so far. We had the mass of the magnesium that we used, which we just now calculated the number of moles. We had the volume of the gas that we collected. We know the barometric pressure in the room. We know the difference of the levels of the liquid inside and outside the eudiometer tube, and we've got the temperature. Well, let's go back to the experiment then and run another trial. Okay, ready here for our second trial. I got a 26 milligram, 0.026 gram sample of magnesium. Let me go ahead and wrap it up like we did the last one. I've got the eudiometer tube sitting over here with another 8 milliliters of hydrochloric acid sitting in it. Get this all wrapped up. Well, let's top it off with a little bit of water. See that hydrochloric acid smoking a little bit there. All right, got my magnesium down inside the eudiometer tube. Top it off a little bit, a little extra water, just to make sure I don't get an air bubble in there. And bingo, into the water bath. Let's clamp it up here where we can see the numbers nicely. And wait for this reaction to happen. I'll try to get a better close-up this time. Oh, there we go. There we go. Okay, well, the reaction's complete. It looks as if we collected, 26.6, I'm going to call it right on the money, 26.60 milliliters of hydrogen gas. Let's take a peek at the height of the water. It looks to be around 216 millimeters above that in the beaker. And it looks as if our temperature is still hanging at 22 Celsius. All right, well, off to the report sheet then. Okay, for trial 2, it was 0.026 grams. So let's do a quick calculation here. 0.026 divided by 24.3 turns out to be, let's put it in scientific notation, 1.07 times 10 to the minus 3 moles. 1.07 times 10 to the minus 3 moles for our second trial. Again, we started off with no bubbles in the eudiometer tube, so we'll start with an initial reading of 0. It ended up being 26.6 on the nose when we finally let the gas cool and read the volume. And so that means that we collected 26.60 milliliters of hydrogen gas. Again, I'll leave it to you to change that into liters. Note that the barometric pressure still was 751 when we ran the experiment. And the difference in the levels inside and outside the tube this time was 216 millimeters of water. Again, we'll come back to this and show how we're going to do the rest of the calculations. Again, the temperature remained at 22 degrees centigrade, so we'll change that to Kelvin also for the second trial. All right, well, let's head back to the chalkboard and see what we can actually do with these numbers then. Okay, so here we are again with the ideal gas equation all rearranged in such a way that we can calculate the value of R given the other 4 pieces here. Now, the hydrogen gas that we collected, the volume of it was very easy to calculate. All we have to do is read that directly from the eudiometer tube. We do need to convert that into liters before we put it into our expression for R, because we like the units to be in liter atmospheres per mole K. The number of moles of hydrogen gas collected is actually equal to the number of moles of magnesium. The reaction is actually magnesium plus 2 HCl's to make magnesium chloride, MgCl2, and 1 mole of hydrogen. So it's a 1-to-1 mole-to-mole ratio. So in essence, all we have to do is take the mass of the magnesium strip we used, in which one case it was 0.024 grams, divided by 24.3 grams per mole, the atomic mass for magnesium. This is only about 1,000th of a mole. Now don't round it off, it'll be 0.001 something something. We're going to plug that in for the moles of hydrogen gas produced. The temperature was easy. We took the temperature of the water bath, and we'll assume that the gas, since it bubbled through the water, would take the temperature of the water bath. And so it's going to be close, within a degree or two. And once you add 273 to that to convert it into Kelvin, which we have to do before we put it into our expression, 1 or 2 degrees doesn't make much difference at that height. Now the pressure, this is where we have to do a little bit of legwork. The pressure of the gas was, since it was collected in the barn here, and the pressure in here today is 751 millimeters of mercury. I should have put that up here as my unit. Millimeters of mercury. Well, there's a couple of adjustments that we have to make to that, because we bubbled it through water vapor. And so consequently, we need to find the value of the saturated vapor pressure of water at the temperature at which we collected the gas, because that gas space in the eudiometer tube is going to become completely saturated with water vapor. Consequently, we need to subtract that out, because we just want the volume of the dry hydrogen, since that's the number of moles that we're using in our calculation. So there's a table in your lab text that shows the vapor pressure of water at various temperatures. I believe the temperature of our water bath was 22 degrees centigrade, so we'll have to look this up in that table when we get to the report sheet and subtract it from our 751 millimeters of total pressure in the lab today. But in addition, if you recall, we measured the height of the liquid that was still inside the eudiometer tube above that was in the beaker. That stretch of water also has to be adjusted for. Now, that's the pressure due to the level difference. This takes a little bit of calculation also. If you recall, it was 248 maybe millimeters of water higher inside the eudiometer tube than in the beaker, but that's not millimeters of mercury. So let me break away here for just a second and explain a little bit more about that pressure due to the level difference. Okay, this correction to the pressure was discussed in the lab text, and it talks about the difference in the height of the water inside the eudiometer tube compared to what's inside the beaker. That weight of water is actually pulling down on this bubble of hydrogen gas that's in here. Remember, this is the trapped hydrogen and water vapor. Well, we need to kind of make an adjustment on the pressure of this gas due to that level difference. So we put a ruler on there and actually measured that difference in millimeters of water, because that's essentially all that's inside that tube. Well, you can't subtract millimeters of water from millimeters of mercury, which is how we've expressed the pressure in the lab. But the density of mercury compared to the density of water is 13.5. It turns out that mercury is 13.5 times as dense as the solution that's inside that tube. So consequently, if we just divide that height difference by 13.5, it would tell us the equivalent in millimeters of mercury. So if you recall, in one of our experiments, it was 248 millimeters from the level of the water in the beaker to the level of the water in the eudiometer tube. We take that 248 and divide it by 13.5 to give us the equivalent millimeters of mercury that we'll subtract from the 751 that was the total in the barn today. All right, back to our original calculation. All right, now that we see how we calculated that pressure due to the level difference, we're going to subtract it off in millimeters, equivalent millimeters of mercury, the same way we did the water vapor pressure. Now, here's the thing though, once we've subtracted these two little adjustments from the 751 millimeters of mercury in the barn, we still need to convert that into atmospheres, which I wrote right here. You have to divide by 760 in order to convert that into atmospheres before we plug it into our expression. All right, so now we have all four pieces: the volume of the gas, the pressure of the dry hydrogen adjusted for the level difference, the number of moles of hydrogen collected, and the temperature we collected it at. Well, let's plug in our numbers on the report sheet and see how this all came out. Well, let's see what we can do here to calculate this value of R, the ideal gas constant. Now, in our first trial, you recall 0.024 grams was our sample of magnesium. We calculated the number of moles, 9.88 10 to the minus 4. We collected this volume of gas. And so changing that into liters, that gives us two of the pieces of information that we need for calculating R, the number of moles of gas and the volume of the gas. Now, the barometric pressure in the lab, or in the barn today, was 751. And in the first trial, the level difference of the water inside and outside of the UDiometer tube was 248 millimeters of water. What we need to do is convert that into an equivalent number of millimeters of mercury. Now, if you recall from just moments ago on the video, it explained that you had to divide this by 13.5. That's the ratio of the densities of mercury and water in order to find this level difference. Now, this is important because this is going to be subtracted from the barometric pressure in order to get our corrected pressure for the hydrogen gas. We're also going to need to subtract the vapor pressure of water. Now, this we can find in a table that was provided with your lab text. And there was a table that just said by temperature that at 22 degrees Celsius, the vapor pressure of water saturated in that UDiometer tube would have been around 19.8 millimeters of mercury. So let's go ahead and put that in, 19.8 millimeters of mercury. Actually, we're only good out here to the tenths, so let's just call it 20 millimeters. And since the temperature was the same for our second trial, let's go ahead and put in the 20 millimeters for it. Okay, so you've got a little bit of legwork here to do. I'm not going to do it all for you. You had to change the volume into liters. Here we're going to have to subtract off this difference in levels in millimeters of mercury. That's the subsequent quotient of this by 13.5. And we're also going to have to subtract off the vapor pressure of the water to get this corrected pressure in millimeters of mercury. We have to change that into atmospheres in order to put this into our expression for R. So again, if you recall, there's 760 millimeters of mercury in an atmosphere. You need to divide by 760. The temperature, which is also what you're going to need to calculate R, is 22 Celsius. You'll have to add 273 in order to get the corresponding Kelvin temperature. Note now that you have the other two pieces of information that we need for calculating R. R was equal to volume times pressure over moles times temperature. And we've marked off all four of those pieces. As a matter of fact, you'll note that they're in bold letters here on the report sheet. So I'll leave it up to you. Calculate your value of R. If you've done it correctly, it should come in somewhere close to that 0.0821, give or take. And again, we've had numbers that ranged everywhere from 0.070 up to 0.090. So there's quite a big window here for you to hit. But again, using this data should give you a decent number for the value of R. And again, just do the same thing for trial 2. Take your average. Now, it's been a while since we did an average deviation. Let me see here. I've got a little piece of paper explaining. For instance, suppose you had your two trials of R, and one came in at 0.0828 and one came in at 0.0818. Well, the average of those two numbers would have been 0.0823, our average R. The deviation is the difference between that average and each of the two trials. And this is an absolute value, by the way. This isn't plus or minus, so they each deviated by 0.0005. Well, if we average those two numbers, they should be pretty identical. The average of 0.0005 and 0.0005 over 2 is 0.0005. Well, to calculate the percent RAD, the relative average deviation, we want to take that average deviation, 0.0005, and divide it by the average R of 0.0823. Well, when you take it times 100, we end up with a 0.61%, at least here in my example. I'll leave it up to you to come up with your two values of R. calculate your average deviation, and calculate your percent RAD. In addition, they ask for the percent relative error. Now this is, remember, a measure of accuracy. Percent RAD tells you only about precision. How well can you hit the same data or the same target point every time? Relative error, on the other hand, asks, well, how close to the bullseye were you? So we want to know the difference between your average R, the accepted R, and divide that by the accepted and take it times 100. That's the relative error. Okay, so we've covered pretty much everything all the way down to the percent relative error. Please don't forget to put a sample calculation for one of the two trials here with R, and put the values that you actually got up here and show me how you calculated it, so I can, if anything went wrong, I can at least see how it went wrong. Now on the back of your report sheet, of course there are some questions. They're sort of like my what if questions. It asks you what would happen if some hydrogen escaped or some magnesium adhered to the inside of the eudiometer tube. So again, do your best bet and give me a little explanation why you think it would be higher, lower, or the same. And again, we've talked about the relative average deviation, the percent RAD, and the percent relative error, and they ask you what it tells you about your data. And number 4, I just want your thoughts on, well, what kind of unavoidable errors might have been in this experiment, and how might they be avoided? So again, give me your best thoughts on that. Now, once you've filled out your report sheet, I'm going to discuss here in a second how I'd like you to get it submitted and when the deadline dates are. So again, make sure you get all your calculations correct and make sure that you show me one sample calculation of R. Okay, since I'm having you submit the pre-lab at the same time as the lab, let me just explain. In question number 1, they gave you a total lab pressure of 752, coincidentally pretty close to what was in the barn, and a temperature of 23 degrees centigrade. You're going to need that to look up the vapor pressure of water. And it said the difference in the levels of solution in inside and outside the eudiometer tube was 185 millimeters. Well, now you've seen that in the video. So you understand you need to divide this by 13.5 to change it into millimeters of mercury. So in essence, you need to subtract from that 752 the result of your division here by 13.5 and the vapor pressure of water at this temperature. You'll have to look it up in the table. Remember, they want the final answer in atmospheres just like we did on the report sheet, so you have to divide by 760. Number 2 is just a straightaway PV equals nRT problem. They've given you the number of moles, the volume, the temperature. That's all you really need to figure out what the pressure on the container would be. This is a Dalton's law of partial pressures problem. Now that means that you have to find the mole fraction of the hydrogen gas out of this collection of gases. And that mole fraction of hydrogen times 1860 will tell you the partial pressure just due to the hydrogen. You may have to go back and reread the section on mole fraction that's in the textbook. Now, number 4, again, it's just a plain ideal gas equation problem, PV equals nRT. They want to know the volume, but they set up dry CO2. So that means that since it was collected over water, you're going to have to go and look up the vapor pressure of water at this temperature and subtract that vapor pressure from the 790 in order to get the pressure of just the dry CO2. That's what you're going to use in the ideal gas equation then to calculate the volume of the dry CO2. And number 5 was pretty much covered in the lab text about using Avogadros hypothesis to derive the actual numerical value for R. And again, make sure that you include your constants on that. Okay, well, my plan was to have this posted by 1 o'clock on Monday the 30th and have it due the following day by 1 o'clock to give you 24 hours to kind of look at the video, fill out the report sheet, and get it in sort of a timely manner so that we don't let this drag on. So again, you've got till 1 o'clock tomorrow. Just take a picture of your report sheet in your pre-lab with your phone, and please don't forget the quiz that I sent you a while back, the one that was on the gas laws that had Charles' law and Boyle's law on it. Please submit that also. And again, each Monday, I'm going to probably send you a flurry of emails in between. But each Monday, there'll be a link to a new lab. I hope there'll be one every Monday. We'll see how this goes. And again, you'll have to submit it within 24 hours. So I hope this wasn't too painful a way to do the labs. At least, you could just kind of sit. And the nice thing is it has a pause button. And if you need to see anything again, you can at least back it up and see it again. So if you have any questions or problems with this, just text me or email me and we'll address them right away. So anyway, I'll see you next week on the internet. So long.